Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So last class we stopped at quasi-static process. Okay. So this is one of the most important or fundamental assumptions that will take for this subject. So I wanted to just briefly go over it again. Okay. So what I meant was that a system remains very close, infinitesimally close to equilibrium state at all the times. Okay, at all the points it is very close to equilibrium, and this process is called quasi-static or quasi-equilibrium. Okay, and we can imagine that the process has to be sufficiently slow. Ideally, when we define, we say that the process is occurring at infinitesimally slow speed. It takes infinite amount of time for that process to happen, such that it is so slow that all the points equilibrium is maintained. So this is one of the very basic assumptions of this subject, thermodynamics. So from now on, whatever processes we will study, this will be an inherent assumption. All the analysis that we'll do, that will based on quasi-static assumption. We assume that the process has undergone quasi-static behavior. Okay. Then we looked at this path. So I hope this is clear to everyone. If any questions, please ask now. Or should I go to chat mode where you can post your questions? So any questions on quasi-static process? Anyone? You can speak up or you can write on this chat box. Okay, I am not getting any message, so I assume that everyone is clear. But if you have doubt, you can, yes.
Sir, please explain the second definition of quasi-static process.
So the definition is this one. Okay, so there are two things you need to understand. Okay, let me get. So that for a quasi-static process, there are two important points. One is that the system remains very close. Okay, infinitesimally, very close to equilibrium. So we assume that all the points are equilibrium points. That is one assumption. Secondly, how that will happen? How I make sure that all my points are near equilibrium? So what I do is I say that the process will take place very slowly, infinitely slowly. So for any quasi-static process, I need infinite time for the process to happen. Okay, so this is just an assumption. So as it is written here, it is assumed to take place sufficiently slowly. Okay, that allows the systems to adjust. Okay, for example, I used the example last time when I said that, let us say you have a piston cylinder arrangement. Okay, if I start heating it from this point, so generally what will happen? The region which is near to the heating point, it will become hot as compared to region which is far from it. Okay, so if you supply a large amount of heat or you heat very fast, this becomes hot, this is cold, right? But if you provide very small amount of heat, if you heat very slowly, infinitely slowly, okay, what will happen is that we assume that at all the times the temperature is uniform within the cylinder. So let us say if this is 100 degrees Celsius, this is also 100. How that will happen? Because I am heating very slowly, so that the system equilibrates. There is no imbalance. Okay, there is no temperature difference at different regions. They should always be at same temperature, these two regions. Okay, so that is the basic assumption of a quasi-static process. Is this clear now?
Oh, yes, sir.
So that's how we plot. So when I plot like this, so when I plot a continuous line, I assume that all these points, whatever points are there, all are under equilibrium states. Okay, any point you take on this curve, this is under equilibrium. That is the assumption of quasi-static process. However, for non-quasi-static path, okay, such as this, what happens is, let us say that this point was under equilibrium, this point was under equilibrium. Okay, I don't know what happened in between. Okay, you can imagine it like this, that let us say this is a xy coordinate of a plane. a person is moving from point A to point B. So if I can plot, I know where he was, I can plot the path. I know what are the x and y coordinates with respect to time, and then I plot this path. Okay, he has moved from here to here. Now for a non-quasi-static path, in this 2D plot, I can only plot.
Sir, your voice is
Okay, let me speak again. Is it clear now? Okay, I'll repeat what I just said. So for a non-quasi-static path, what will happen is that I know that this, let us say this point was under equilibrium and this was under equilibrium. In between what happened, I don't know, because it did not went through equilibrium processes. I don't know how it went. It went like this, or it took a path like this. Whatever path it took, it cannot be plotted in this 2D plot. Okay, so to able to plot the process in this XY plot or whatever properties, I need to have all the points as equilibrium states, which will happen in quasi-static, but not in other processes. Is this clear, everyone?
Yes, sir.
yes, sir.
Fine. Let us move now. So anyway, we'll also look at some examples. So next chapter also, basically all the processes that we'll talk about from now onwards, in particular in this course, we'll assume that they are quasi-static. So this is an assumption. As you go along, you will see that all natural processes or engineering processes, they are not, strictly speaking, not quasi-static. That is an assumption. For example, no process takes infinite time to happen. All the processes happen at finite time. They work at finite rates. But this is an assumption. For example, when you say ideal gas assumption for air, okay. So for numericals, we'll assume that air is an ideal gas, which is true for, which is a good approximation for a lot of conditions. But there are conditions where this is not a good approximation. Similarly, we'll assume quasi-static path for a lot number of cases, and we'll see where it is not a good assumption. That we'll talk about. So now let us see what are the types of processes generally we'll see in this course. So we could have isobaric process where pressure is constant. Isochoric is the name given for a constant volume process, and isothermal where temperature is constant. Let us see how we can plot these processes in a PV plot. So in a PV plot, what it will be? Constant. What is constant here? Can anyone say?
Pressure.
Pressure is constant. Yes. Yes. So this is isobaric. Similarly, this is a constant volume process or isochoric. What about this one? What is constant?
Isothermal.
Constant temperature, isothermal.
Yes.
Temperature constant.
Isothermal.
Temperature is constant. So we have thermal process.
If it is ideal gas.
Yes, if it is ideal. So that will be basic assumption. Generally, if I'm not stating otherwise, it is understood that it is an ideal gas, it is undergoing quasi-static process. That are the very basic assumption for now on. Okay. Now let us talk about a cycle. Okay, so let's say that we have a PV plot. A system is at point 1 and then it takes a path A and goes to point 2. Now if I want to come back, okay, so I can take another path B, which will take me back to the initial starting point. Okay. Now path A and path B together form a cycle. So there could be 2 paths, there could be 3 paths, there could be 10 paths. But the important point is that I'm going back to the initial starting state. Okay. So a system is said to have undergone a cycle if it returns to its initial state at the end of the process. So it doesn't matter how many processes are taking place, but at the end of the cycle, it should be back from where it started. That is the basic definition of a cycle. Okay, and cycle could be of any shape or any number of processes. So at least it should have two. One should be forward, one should be backward. It could have also have three. Two we have seen the last slide. Here we have seen three. So this is one process, 2, 3. Similarly, we have 4 processes, or we could have n number of processes. We can also draw a polygon here or any irregular shape. Okay, we don't care much how the process looks like, but it should be, as I said, it should be under a quasi-static process. It should be always under equilibrium, and we'll see how to define a different or very irregular shape. Okay, but whatever shape you give, whatever is the number of processes that are taking place, if it returns back to its original condition, original state, then we can say that this is a cycle. Okay, so this is the important point. You have to go back to the initial state. That's all. So with that, we finish this second topic. These are the reference books that I have already mentioned. With that, I will stop. Okay, so we'll go to the next chapter now. Let me stop the recording for this.